Here's a program that asks your computer to do the same work billions of times for no reason. Computing the 50th Fibonacci number the obvious way takes over 20 billion function calls. The smart way takes 50. Same answer, same formula, one tiny change. That change is dynamic programming, the technique that feels like cheating, and the one interviewers reach for the most. In the next few minutes, you'll see exactly why the naive version explodes and how one notebook makes it vanish. This is Logic Lab, where computer science becomes something you can see. Today, what do you do when you'd otherwise solve the exact same subproblem 1,000 times over? Take Fibonacci. Each number is the sum of the two before it. So to get Fibonacci of 5, you need Fibonacci of 4 plus Fibonacci of 3. Simple, just call the function on each and let it call itself. But watch the tree of calls it spawns. Fibonacci of 4 also needs 3 and 2. 3 needs 2 and 1. And here's the disaster. Fibonacci of 2 gets computed again and again and again, the same answer recomputed from scratch every single time. The tree roughly doubles at every level, so the work grows like 2 to the n exponential. By the 50th number, you're drowning in billions of redundant calls. The information is the same. The computer just keeps forgetting it. So give it a memory. The first time you compute Fibonacci of 2, write the answer in a notebook. A lookup table we'll call the memo. One new line of code. Now, before doing any work, the function checks the notebook. Already solved. Just return the stored answer instantly. Watch the giant tree collapse. Every repeated branch becomes a single lookup. This is memoization, or top-down dynamic programming, ordinary recursion plus a memo. Each subproblem is solved exactly once. The cost crashes from exponential 2 to the n, all the way down to linear O of n. There's a second flavor that flips it around, tabulation or bottom-up. Instead of recursing down from the top, start at the base cases and build upward, filling a table one cell at a time. Fibonacci of 0 is 0, of 1 is 1, write those. Then each new cell is just the sum of the two before it, left to right across the table. No recursion at all, just a simple loop. Same linear cost, often a little faster. But dynamic programming only works when the problem has two properties. First, overlapping subproblems. The same smaller questions come up over and over, the way Fibonacci of 2 kept reappearing. Second, optimal substructure. The best answer to the whole is built from the best answers to its parts. Spot those two signs in an interview, and dynamic programming is almost certainly the intended tool. And it's everywhere these problems hide. The shortest edit between two words your spell checker uses, counting the ways to make change, finding paths through a grid, even aligning DNA. All of them the same idea, break it down. Remember what you've already solved. That's the whole mindset. Trade a little memory for a lot of time and never solve the same problem twice. It turns the impossible into the instant. Recap. Naive recursion resolves the same subproblems and explodes to 2 to the n memoization, adds a notebook so each is solved once, top down. Tabulation builds the table bottom up with a simple loop. Both need overlapping subproblems and optimal substructure, and both turn exponential into linear. Dynamic programming leans on a function calling itself, and that idea, recursion, is secretly everywhere in code. How does a function call itself without spiraling into chaos? That's next on Logic Lab. See you there.